All right, so good morning. Welcome back. The plan for today is to get through section 6.3 and 6.4 and maybe get started on 6.5. So we'll talk about factoring special products and then kind of a general strategy for factoring polynomials. So this will be kind of a recap of factoring. I think what we're going to do here is I have maybe 5 or 6 problems, and uh, I'll kind of just open it up to you to, give you 10 minutes or so, 15 minutes to work through them. And then we'll kind of quickly go through the answers and answer any questions you have. And that'll pretty much wrap up the basic discussion of factoring, and then we'll apply factoring to solving polynomial equations. I was working outside yesterday for a little bit, so my allergies are going a little haywire today. The quote of the day or idea of the day today is don't underestimate the impact of survivor bias. And because of our shortened class time and how much we have to get through today, I don't want to talk too much on this, but kind of long story short, I saw this face or YouTube short this past weekend where somebody had posted about Arnold Schwarzenegger's workout program, where he does, like, on Shoulders Day, he does like 35 sets of several different exercises, and people in the comments were basically saying, yeah, like, I tried Arnold's workout. Like, he would say, he published what he used to do, and they're like, yeah, I couldn't do it. Like, everybody was saying, yeah, I tried it and ended up injuring myself all the time, or I was so fatigued that I couldn't do anything else, or I couldn't recover for the next workout or whatever. And so if we're looking backwards at the successful people, there were probably 1,000 people like Arnold who could have been Arnold, but maybe, you know, uh, just basically got lucky and didn't get injured, or who, were able to handle all of that volume. So if you're looking backwards and you say, hey, I want to be stronger and have better physique, like Arnold was strong and had a great physique, like, maybe I should do what he does. Well, what he did worked for him and he was at the pinnacle. It's probably not going to work for you, right? So he was kind of the survivor. He was of all of the people who went through that such a crazy demanding workout program, probably 999 out of 1,000 got injured or couldn't handle the fatigue or whatever, and Arnold is the one out of 1,000. Or in a different application, the author of Rich Dad, Poor Dad, great book. It has a lot of great advice in it. The author, Robert Kiyosaki, his basically financial strategy, if you want to call it that, when he was younger, was go out, buy up a lot of property, get yourself into a crushing amount of debt, and use the fact that that if you don't find a way to make those monthly payments, then you're going to have all of these people calling you, bankers calling you and bugging you, and it's going to be like super stressful. So use that as your drive to find a way to make those payments. Again, it worked great for Robert Kiyosaki. He's probably a multimillionaire by now, well, many times over. Um, he's near the end of his career at this point. But my feeling is that I don't have data on this, but my feeling is there are, for every one Robert Kiyosaki, there's probably 1,000 people who did a similar thing, and just crashed and burned and, had a nervous breakdown or couldn't handle the stress or just filed for bankruptcy or whatever. Um, so yeah, it looks nice when you look at the result of Robert Kiyosaki, but then you say, well, wait, I wonder what the likelihood of this is actually working. He was the survivor, the success story, and all the people who crashed and burned, well, they don't write books about it, right? All the people who, like, could have been Arnold in some sense, but ended up blowing out a knee and, are a personal trainer in a local gym now, nobody reads their books, or they don't write their books. We read about Arnold. So just keep in mind that survivor bias is a very real thing. And, uh, if you're looking for inspiration, looking to somebody like Arnold or Kiyosaki or any of these successful people is great, saying, hey, I could be like that person. They started off where I am and they ended up where they are. That's really cool. If you're looking for, I think it's like inspiration versus aspiration, people talk about. If you're like, I want to be Robert Kiyosaki, so I'm going to start walking exactly in his footsteps and do exactly what he did. that's probably not such a great idea, right? If you see the accountant down the street, and you say, "Hey, how did you become an accountant?" And you have much more. It's much more likely that if you set your sights on being a successful accountant in your local neighborhood, that the probabilities are much more in your favor, right? Um, okay, so moving on to factoring special products. So some uh, we saw some ideas related to factoring trinomials. So quadratic polynomials with the highest degree being degree 2, like this one. And we're going to look at some patterns that come up occasionally that if we recognize this pattern, it makes the factoring process a little bit easier. So the first one we're going to look at is perfect squares. So if I think of multiplying out or foiling a plus or minus b all squared, be really careful. It's easy to look at this and then write it as like a plus or minus b, or sorry, a squared plus or minus b squared. But we know that there's a cross term, right? So we do need to be a little careful about that. So we know that there's this cross term. The outers and the inners are going to contribute, but a plus or minus b all squared gives me a squared plus or minus 2ab plus b squared. So basically, what I'm looking for in this pattern is that 2 of my 3 terms are perfect squares. So I have 3 terms, 2 of which are perfect squares. If I recognize that if I see that I have 3 terms, 2 of which are perfect squares, then that points me in the direction of a perfect square trinomial. Now, if I have a candidate, if I have 3 terms, 2 of which are perfect squares, it might not be a perfect square trinomial. The cross term still has to work out correctly. The cross term still has to be plus or minus 2ab. So I still do need to check that it's the case, but if I look at an example like this, I have 3 terms, so I have a trinomial. 49x squared is 7x all squared, and 121 is 11 squared. So I see that 2 of my 3 terms are perfect squares. So it fits this pattern, at least the kind of initial indication of this pattern. And then my my question is this cross term right? So I could have this cross term, this x to the first term or the linear term, lots of different names for this one. I could have it lining up just right so that I do have a perfect square trinomial, or it could not mesh. It could not match up nicely with the other 2 pieces, and it's not a perfect square trinomial. So let's check. Okay, so my first term I'm saying is a squared, or that's 7x all squared. So a would be 7x. My last term I'm saying is b squared, or 11 squared. So b would be 11. So my question then is, what is 2ab? I see my cross term in my perfect square trinomial is 2ab with a plus or minus, but the important part is 2 times a times b, or 7x times 11, or 2 times 7x times 11. Well, that's 77 times 2 is 154x. And 154x is exactly what we have in our cross term. So this is going to be, I see I have a plus here. So that's going to associate with a plus over here. And I see this is going to be a plus b all squared, or 7x plus 11 all squared. Right. For this problem, I mean, look at this A and this C, 49 and 121, it would be a real hassle to do, say, AC grouping method or something like that. But because I recognized that it was that it started to fit into that mold anyway of a perfect square trinomial, I was able to check my cross term, verify that my cross term does indeed come out correctly, and pretty easily write the factored form here. Oh, I don't know why that happened. Okay, give me 1 second here. Okay, so let's look at this next one then. So I'm going to copy down my formula here. All right, so I see 64y squared minus 16y plus 1. And again, I'm always on the lookout for these special products after this section. So I ask myself, okay, well, I have 3 terms. Do I have 2 of them that are perfect squares? And yes, I do. I see that 64y squared is 8y all squared. And 1, of course, is just 1 squared. 1 can actually be one of the easiest perfect squares to miss, because a lot of times we just think of 1 like, oh yeah, that's just 1, but it actually is a perfect square. So 1 squared is 1. So matching this to our pattern up above, we have that A is 8y and B would be 1. Now we still don't know if the cross term is right, so let's check it. For this to fit completely into the mold of a perfect square trinomial, we're kind of suspicious at this point, but we need to check that cross term. We need to check what is 2ab, or that's 2 times 8y times 1, or 16y. And I do see that my cross term minus 16y does fit that mold. The sign of the cross term isn't important for whether it fits the mold. It's just the value of the cross term. So the 16y, that is what I get. It does fit. Now this sign is what tells me the sign of my binomial in the factored form. So I have an a, 8y, and then here I have a minus 1, all squared. Or even something like this that's pretty complicated looking. I have some r squared, some s squareds, an rs term. But still, I notice that I have a trinomial of 3 terms. I have 2 of them that are perfect squares. 5r all squared and 6s all squared. Again, as usual, I still don't know about the cross term. So that's what I'm going to check now. If this fits into that perfect square trinomial pattern, then A would have to be 5r and B 6s. And as a side note, if you picked your A and B the other way, it doesn't matter. So we need to check 2ab, the cross term. If it does come out right, then we do have a perfect square trinomial. If it doesn't, then we don't have a perfect square trinomial, and maybe we need to try something else. So 2ab would be 2 times 5r times 6s, or that's 60, 2 times 5 times 6 times rs. And it does work. So my cross term does match. So in my factored form, I have 5r as one term, 6s is the other term, all squared. And how do I decide what sign connects them? I look at the sign of my cross term, negative here, 5r minus 6s all squared. Minus ended up being a little too big there. There we go. Any questions on perfect square trinomials? So for these pattern matching examples for these special products, we just kind of need to know some formulas. We need to know this formula or have it available to kind of match things up to. And if we forget the formula, we can always recover it by remembering, okay, if I want something to be a perfect square, it's got to be like a plus or minus b all squared, and then just multiply it out, just FOIL this out, collect like terms, and that's what you get. Okay, so the next pattern that we're going to look at is the difference of squares pattern. And here we have something that almost looks like the perfect square trinomial. But the difference is, instead of having, say, a plus b times a plus b, or a minus b times a minus b, we kind of have one of each factor. We have an a plus b times a minus b. And it turns out that when we multiply these together, our first give us a squared, our outsides give us minus ab, our insides give us plus ba. Well, but that's just the same as plus ab. And our last give us minus b squared. The cross terms completely cancel out. Instead of them kind of adding together in the same direction, either plus and plus or minus and minus, as they did in the perfect square trinomial, in the difference of squares polynomial, one goes in one direction, one goes in the other direction, they end up canceling out. And I just get a squared minus b squared. So this is one that, at least in my experience, comes up a bit more often than the perfect square trinomial, difference of squares, a squared minus b squared. And so again, if I'm looking at a polynomial like this, I'm looking for a polynomial with only two terms. That's one of the big things that makes difference of squares look a little different than usual. And I'm looking for both terms to be perfect squares. So 169y squared minus 1. Well, 169 is 13 squared. So 169y squared is 13y all squared. And 1, of course, is just 1 squared. I do have a difference of squares. So this tells me that this is going to factor into 13y minus 1 times 13y plus 1. Now, it is important to get things in the right order, because this a minus b, the minus b has to be associated with the minus b squared term. So we do have to make sure to get things in the correct order. Up here, it didn't so much matter because, well, a minus b all squared, well, that's the same as negative 1 times b minus a all squared, right? But the product of two things to the second power is negative 1 squared times b minus a all squared. The negative 1 squared goes away. We see that switching the order in the perfect square trinomial, it doesn't really matter. That negative 1 gets squared off. But in difference of squares, it is important that we have kind of our a's and our b's sorted out properly so that we have the correct thing we're subtracting from and the correct thing we're subtracting off in this this factor here. Now, a side note, we might say, okay, if there's a difference of squares, if there's a difference of squares pattern, is there a sum of squares pattern? A squared plus b squared. And the short answer is no. The short answer is that sums of squares don't factor. Take a very simple one like x squared x squared plus 1, and we can still apply our general quadratic strategy to this. X squared plus 0x plus 1, I'm looking for two numbers, m and n, that multiply to 1 and that add to 0, good luck finding a solution to that, right? The product has to be 1, positive 1. Really, the only choice is m equals 1 and n equals 1, and m plus n is 2, not 0. So we can see this is a counterexample. We can't say that the sum of two squares is going to factor, and in fact, it doesn't factor. It's not just this sum of two squares example that I picked here that's problematic. In fact, none of them are going to factor. So sum of two squares don't factor, but difference of two squares does factor. In the perfect square trinomial, this cross term could be a plus or a minus. But in our difference of two squares, we have to have a squared minus b squared. Only this structure with the minus connecting them factors. With the plus connecting them does not factor. Okay, another example. Factor 49x squared minus 81y squared. Well, here again, I look at my first term. I see that it is a perfect square. It's 7x all squared. I look at my second term, 81y squared. That's 9y all squared. And they're connected with a subtraction. Well, this is going to be 7x. And again, for my minus factor, I need to make sure they're in the right order. 7x minus 9y times 7x plus 9y. And last example in this subsection. If I look at this, at this binomial here, it doesn't really look at all like a difference of squares. 98, I don't recognize that number as a perfect square, nor 72. I mean, I have an r cubed and an r, neither of those look like perfect squares. However, if I look at this, I might say, well, you know, the way it looks right now, it's not a perfect square, uh, a perfect square polynomial. Sorry, it's not a difference of two squares polynomial. But there's a little bit that I could do in advance. Something that I always want to check in my general strategy is whether there's a greatest common factor that can factor out. And in fact, I see that I can factor out an r. And well, 98 would be 2 times 49. And 72, 2 times 36, I can factor out a 2. So I can factor out a 2r. That gives me 49r squared minus 36 that's remaining. And now I do recognize this as a difference of two squares. So I can write that 49r squared as 7r all squared, and 36 as 6 squared. This 2r out in front is just kind of coming along for the ride. It's already factored out. We're just looking at, can I continue factoring? And this difference of two squares turns into a 7r minus 6 times 7r plus 6. So in any of these special products or special factor, special products or special factoring patterns, I have my kind of base pattern. I might recognize that at the very beginning of the problem, but I always want to take a look and see if there's a greatest common factor that can factor out. If there is, I can factor the greatest common factor out, and then maybe one of these special patterns, you know, comes forward and it's more visible. And we saw before in a previous section that factoring a GCF out at the beginning also, even if it's not one of these special products, it also just makes the factoring process a lot easier. So it's good to get ourselves kind of in the habit of just checking for a greatest common factor first. So if we go back through, none of these had a greatest common factor to factor out, but it's a good thing to just keep an eye out for. Not until we got down here, and here we did have a greatest common factor. Okay, and then lastly, our sum difference of cubes. So if I have a cubed plus or minus b cubed, so we have the difference of squares that factors, but the sum of squares doesn't factor. But for cubes, when we have two terms, both of which are perfect cubes, the sum or difference, both of them factor. They factor this way. So a cubed plus b cubed, we can factor out an a plus b, and then times a squared minus ab plus b squared. So this plus or minus symbol here versus this minus or plus symbol here, the plus or minus meshes with the minus or plus in the sense that this symbol has to be the opposite of this one. So if you put a plus here and a plus here, this will be a minus. If you put a minus here and a minus here, this will be a plus. And then this last one here is always a plus. Now, to be completely honest with you, I never remember the sum or difference of cubes formula. There's a particular way that I remember this. It's a little bit linked to polynomial equations, so we'll get a little more insight there. But basically what I remember is that for a cubed plus b cubed, I can factor in a plus b out. And for a cubed minus b cubed, I can factor in a minus b out. And then I just kind of work out what these terms need to be. So I like going that approach. It's a little less memorization. But if you like memorizing the formula, you can do that as well. And regardless, I would recommend checking at the end of this, just, multiplying back out and making sure that all of the right stuff cancels out and you're left with your original polynomial. So let's look at factoring x cubed plus 27. So I do see that I have a sum or difference of two cubes. I have x cubed, which is obviously a perfect cube, and 27, which is 3 cubed. 3 times 3 is 9. 9 times 3 is 27. And I have a plus connecting them. So a here is going to be x, and b here is going to be 3, and I have the sum of two cubes, so this is going to factor as a plus b, x plus 3, times a squared or x squared. And then I have to switch the sign between these two, minus ab, or 3x, plus b squared plus 9. Now, something kind of interesting about sum or difference of cubes, this quadratic that we get here never factors any further. It's just the way that it turns out. So x squared minus 3x plus 9, I can't factor that any further. This is going to be prime. So this would be my fully factored form. And let's just double check that everything works out. If I distribute the x into the trinomial, x times x squared is x cubed minus 3x squared plus 9x. And then if I distribute the plus 3, I get a plus 3x squared plus 3 times negative 3x is minus 9x. And then plus 9 times 3 is plus 27. These go away, those go away, and we get x cubed plus 27, which was exactly what we started with. So just because there's so much going on here and it's easy to get a sign wrong somewhere, good to just kind of check things at the end. Okay, so then what about y cubed minus 216? So pretty similar. I see a equals y, right? Y cubed is obviously a perfect cube. 216, well, what could that be? I mean, 4 times 4 is 16, times 4 is 64. So we need to go a little higher if this is going to be a cube. I see the y cubed, so I'm hoping for a difference of or a difference of cubes here. 5 cubed, 5 times 5 is 25, times 5 is 125, getting closer. What's 6 cubed? 6 times 6 is 36. And 36 times 6 is, well, that would be 180 plus 36. That is 216. This is 6 cubed. So b equals 6. So here I do have a difference of 2 cubes. So I can factor it as a minus b, y minus 6 times, well, a squared is y squared. My sign has to change, so my minus changes to a plus. AB, be really careful here. It's not plus 2ab, it's plus ab, plus 6y, and then plus b squared, plus 36. And like before, I don't have to check this remaining quadratic, and it's always going to be prime. Now, normally, if I just kind of factored out a linear piece and I had a quadratic piece left over, I would want to check that quadratic piece as well and see if it can continue factoring. But in this case, this is always going to be prime when we fit the sum or difference of two cubes pattern. And just like before, let's double check by multiplying out. So y times y squared is y cubed. Y times 6y is plus 6y squared. Y times 36 is plus 36y. And then distributing the minus 6, being careful with the sign, minus 6y squared. Minus 6 times 6y is minus 36y. Minus 6 times 36 is minus 216. These go away. Those go away. And we're left with exactly what we started with. And then last but not least, we have this example here. Factor, say, 2 minus 16x cubed. And here I have two terms. So I'm thinking along the lines of maybe difference of two squares or sum or difference of two cubes. I see that I have an x cubed. So that might make me think of difference of two cubes, but my 2 and my 16 don't cooperate with that. Right? 2 is not a perfect cube, 16 is not a perfect cube. Alternatively, I see that I have a difference and I have a 16, which is a perfect square. But for this to be a difference of, oh, how did that happen? For this to be a difference of two squares, well, my x cubed would, that's not a square. That doesn't mesh nicely. And my 2 is not a square. But again, I can recognize that I can factor out a common factor. I can get 2 times 1 minus 8x cubed. And now the pattern reveals itself. I see 8x cubed is 2x all cubed. And 1, of course, just like 1 squared is 1, 1 cubed is also 1. So I have 2 times. Here I have a is 1 and b is 2x. Let me bring my formula down here. So I have the difference of two cubes. So I'm going to have a minus b, or 1 minus 2x, in this first factor, and in my second factor, a squared, or 1. My sign changes to a plus. AB is 1 times 2x, or just 2x, and then plus b squared. Note that 2x all gets squared, so that's going to be 4x squared. And that's as far as we can factor it. Again, this is prime. That's always going to be the case with summary difference of two cubes. This piece here is always going to be prime. We have our greatest common factor, that 2 that factored out, and then the bit that came from the difference of two cubes. And here, ideally, we would like to multiply and check, but I'll leave that as an exercise. Okay, so let's discuss the general strategy then for factoring polynomials. So if you come up to a polynomial and you see it for the first time, you don't know what section it's in, you don't know what strategy you should apply. Here's a nice little flow chart from the book. Let me actually make it a little bigger. Little flow chart from the book that can be kind of a helpful guide. The very first thing we're going to do is look for a greatest common factor. Is there a factor that's common to all terms that we can factor out? If there is, we should do that right away. That's going to make everything that follows a whole lot easier. After that, we're going to ask, is this a binomial? Does it only have two terms? If so, then we're looking for either difference of squares or sum or difference of cubes. Remember, sum of squares does not factor. Is it a trinomial? Is it something with three terms that is a quadratic function that has degree 2? Well, if it is, then we do our m and n thing, right? We're looking for m and n such that m times n equals c and m plus n equals b when our leading coefficient is 1, or when our leading coefficient is not 1, we look for the AC grouping method. We look for m times n equals a times c and m plus n equals b, and we break apart that middle term. Or if we happen to recognize that our quadratic fits the perfect squares form, that pattern, then we might look for we might look at that cross term and see if everything works out. And if it does, we get our factorization more easily. And if we have more than 3 terms, so if we have 4 terms or more, we would look at factoring by grouping. So here I have 6 polynomials, and I want you guys to go through kind of as an exercise and try to factor them completely. So I think what I'll do is I'll leave all 6 up on the screen here, and we'll take maybe about 6 minutes. And in 6 minutes, we'll kind of just come back together, touch base. We'll work through the answers for the first 3 problems, and then we'll continue on for another maybe 5-6 minutes, and then we'll touch base and work through the answers for the last 3 problems. So start working your way down. If you get through all 3 in 6 minutes, great. If you don't get through all 3 in 6 minutes, it's not a big deal. This isn't, exam day or anything like that. But just for the sake of time, we're gonna not give a ton of time to work on these. But we'll take 6 minutes on these first 3, and then we'll come back and discuss them. Okay, it's been about 6 minutes, so a few minutes in, I put a couple of hints up here in case you were stuck on any of these. I also tried to smush these a little more on the screen so that we could get the uh, strategy diagram up there. So let's expand these back out and take a look at them. Okay, so the first one, do I have a greatest common factor? Well, I don't have any variable common factors because I have a constant term, an x term, and an x squared term. And the numbers 2, 13, and 7 don't share a common factor, so no greatest common factor to factor out. I do see that I have 3 terms. It does not look like the perfect square pattern. I don't see 2 terms that are perfect squares. So I'm going to use AC grouping. I see that A times C is 2 times -7 or -14, and I'm looking for numbers m and n so that their product is -14 and their sum is b or +13. And I might be able to guess. I know that the product being negative means one has to be positive, one has to be negative, and their sum is 13. So I think that m is 14, n is -1. That product gives me -14, and the sum gives me +13. Now remember, in AC grouping, this doesn't tell me that I have something like, x plus 14 times x minus 1. It doesn't give me the factorization right away. It tells me how to break up this middle term. I have 2x squared plus 14x minus 1x. So the 13x is 14x minus 1x minus 7. And let me come around this down to here. From my first 2 terms, I can factor out a greatest common factor. I have a numerical factor of 2 and a variable factor of x. 2x times x plus 7. And then I want something that looks like an x plus 7 coming out of these last 2 terms. So I'll factor out a -1 or just a minus x plus 7. And now I can factor out an x plus 7, leaving me with 2x minus 1. And all of these, whenever I factor them, I should go back through, multiply out, and check. I'll leave that as an exercise to do. X to the 4th minus 81. I don't see any greatest common factors. One term has only variables, the other only numbers. So no greatest common factor. I see that it's a binomial. It is only 2 terms. So I'm looking for something like difference of squares or sum or difference of cubes. And here I do see that I have a difference of squares. I have x squared minus 9 squared. So I'll call x squared a and 9b. So x to the 4th minus 81 would be x squared minus 9 times x squared plus 9. But I factored this, and I ended up with at least one factor, in this case, both factors, that are still quadratics, that still could maybe be factored further. I always want to, when I get a factorization, to check and see if anything else can factor. Is there a greatest common factor I can pull out? Maybe I just forgot it or missed it on the first go. Maybe I catch it on the second time around. Well, here I have a quadratic. It's a binomial. It's a sum of squares, and we know those don't factor. Okay, so x squared plus 9 is as simple as it can get. But x squared minus 9, though, well, that's a difference of squares again. So x squared minus 9 is obviously x squared, so a is x. Minus 3 squared, b is 3. X squared minus 9 actually factors into x minus 3 times x plus 3. And then that multiplies x squared plus 9. Now that's our fully factored form. This cannot factor any further, nor can that. Those are both linear factors with no greatest common factor to pull out. and my sum of squares does not factor. And then lastly, let's look at this one, 8x squared minus 9x minus 3. So again, AC grouping method. I check for common factors. There's no greatest common factor to factor out here. This doesn't seem like it fits into any of the special categories like perfect square, trinomial. So I'm just going with AC grouping method. I'm looking for an M and N whose product is negative 24 and whose sum is negative 9. So I know that their product being negative means they have to be opposite signs, and their sum being negative means that the larger magnitude number has to have the negative sign. So I could have 1 times 24. I would need that 24 to be the negative one, the negative number. But M plus N gives me negative 23, not negative 9. 2 times negative 12, that would be a possibility. But this gives me negative 12 plus 2 is negative 10. Nope. 3 times negative 8. Negative 8 plus 3 is negative 5. 4 times negative 6. Negative 6 plus 4 is negative 2. Going up to 5, that's not a factor. And we go up to 6. We've repeated. We get 6 times 4. So there actually is no combination of M and N that satisfies both of these, the product being negative 24, the sum being negative 9. Our AC grouping method, I guess you could say, fails. Failed successfully, I suppose. We have determined this one is prime. It's a little bit like this x squared plus 9 or something like that. It doesn't factor any further. That just is what it is. We can't factor it over the integers. Okay. And then maybe we have only 4 minutes left. So maybe actually, here's what we'll do. For next time, write down these 3 problems if you didn't get to them yet. If you did get to them, great. But for next time, write down these 3 problems in the next minute or so. And then next time we'll start off by just working through these, but try to work these out in between this class and next class. And yeah, the first thing we'll do on Thursday, we'll run through these. We won't do much in the way of warm up because I'll expect that you've already worked through them and that you've already attempted them and that most of you will have an answer for each of them. So we won't do a whole lot of warm up, but we'll just jump right into these 3 next time, and then we'll continue on to polynomial equations. So write down these 3 problems, and over the next couple of days, go through them, work through them, try to figure out. And this flow chart is in your book. So if you want to refer back to it, just take a look in the book. Apply that to these 3 problems. Be a little careful with this one. The GCF, does come into play for that one. And then we'll pick up with these on Thursday, run through these, and then continue on with polynomial equations. Okay, I will stop the recording.